So this, on Monday, we walked through this lab, got everybody to be able to do this. And then what I want to do is go over the, kind of bring it full circle. So the way that projectile motion started, it started with that vector displacement triangle idea, all worked out in the textbooks. Then in this trinket, we actually used forces to talk about that, and went from forces to 1D kinematics to push that, or 2D kinematics just handled by vectors in one dimension at a time. And so that's a different approach than the by hand kind of textbook way of looking at it. So what I want to do today is take the data from this lab, and I sent out a PDF. I actually had to, I left a slide off, and so I fixed it over lunch period. So there's a new one there if you want to use that. You're not required to take notes on this. This is just explaining how this works. And so here's this nice little thing from there. And I want to remind you, we had this data here that said that because of the way we built the ground and the ball, it was actually above 0 because the ground is at 0, 0 level. I suppose we could have put the ball at 0, 0 and it'd be more like what we do on paper. So the goal here, besides coming full circle with a lab that literally expands the whole course so far, is to, one, bring it back and verify that this model works, and then two, show the difference between, say, physics and reality, because the simulation is closer to reality than the by-hand analysis would be, because we assume all of the simplest, most luxurious things when we do it on paper, all right? And so kind of want to wrap that up, put a pin in it. So here's the first graph, the height above ground graph. And so we could talk about, in this one, we could talk about time of flight, all right? So if we wanted to have that discussion, let's talk about time of flight and see what we can get from this graph. Well, right here is the time of flight. If I go all the way to the end of this path, so this parabola matches the trajectory, at least. It was a little bit more spread out on the screen, but just because of the way that it's scaled versus this graph. This graph is fixed to a particular horizontal width that isn't realistic to the range, because we're doing time here instead of range. And it was 0.577 seconds. And so what we could do, and we will do, is does this match the reality, or I'm sorry, the physics of if I take the speed, which was known to be 4, that was our assumption, gravity is going to be 4.9 t squared, and where do I get that? I get that from 1/2 gt squared. G is 9.8, half of that is 4.9, so 1/2 gt squared is 4.9 t squared. In the textbook, we did a lot of 5 t squared, just assuming that g was 10, just for nice, pretty numbers, okay? And we had an angle of 45 degrees. Those were all known things from the givens in the assignment. And so since I have an opposite and a hypotenuse and an angle, I can know that the sine of 45 degrees would be opposite over hypotenuse, which means that it's 4.9 t over 4, and so t would just be 4 sine 45 over 4.9, and that's roughly 0.577 seconds. So the theoretical, meaning what's written in pink, the textbook stuff, is a great match to what we put into this simulation. And the simulation didn't have the same math that we did on paper. The simulation was, if we pretend that the only weight force, or the only force on the ball is its own weight, okay, then I suppose in some way, since this is half g right here, we're in some way accounting for the gravitational force, all right? But then we went on to find the acceleration so that we could update the velocity, okay? And the velocity is sort of bottled up here, okay? But we didn't use the angle in any of that math because we didn't have to. Well, I take that back. We did pass it into the velocity definition function. And so even the angle was buried in there, but the way that we input it wasn't the same as this triangle. But this triangle, this vector displacement triangle for projectile motion, accounts for those same things, but in a very different way, okay? And so it should work out in this case, and it did. So we have time of flight here for that. Now we could also talk about this right here. This is the time at peak height. Got to spell height right. All right, and if we look right here, 0.288 is going to be half of that 0.577. And so we could verify the max height. So max height, that mathematics, we did that in a calculator on Monday when we were working that. And that formula was initial height plus v naught squared over 2g sine squared theta. And if you remember from Monday or on the first screen here, the initial y height was 0.06. The speed is 4, so we'll just square that. 2 times 9.8, 19.6. And then the sine of 45 squared, which is sine of 45 and cosine of 45 are root 2 over 2, so some number there, 0.707. And if you run all of this out, you get 0.4681. Now, here's why there's a little bit of offset, because in the instructions I told you let that be 0. That was just for the sake of the calculator. And so in that calculator part of this Trinket Lab, we let that be 0 so we didn't have to bother with extra inputs. We just wanted to keep it simple and classical because we always assume it starts at ground level. But ground level, if that's 0, when do you kick a ball that's already in a hole at its exact halfway point? That's not reality. It's shifted up, all right? And so if we were to, subtract that from here, we'd get 0.4081, which would be off a little bit, more than we like. So we don't, we don't bother with that. So that's sort of, we verified that, yeah, this graph, it matches well with the reality of the graph, which is part reality because we made some assumptions for simplicity, is very, very close or spot on with just the pure math theoretical side of this. And so it doesn't matter what branch of science you are mastering, they all work this way. There is a theoretical part that is the on-paper textbook perfect world scenario. And then there's the messy reality of life that has all of these little offsets in it that you have to account for. You're going to use the ideal model as the foundation of how you account for all of the little shifts in reality. So whether it's physics or chemistry or biology, epidemiology, whatever it is, all sciences have that feature going for them. And so you learn it here, you transfer that skill to the next thing. All right, position along the ground. So we could talk about the range here. This would be the horizontal thing going on here. And so the range, we could compute it a number of ways, but we have it right here on the graph. The change in x, that is the range, okay? It will be x minus its initial thing, and in this case, it will be the range, okay? So we could put in here the final x value was 0.672 minus the initial x value of minus 0.96. And if you crunch those numbers, you get 1.629, which will verify another way. And one way to do that would be to use that vector triangle. So that would be the range that I want to compute. And this was for t, which we know what t is now. Okay, so we could say cosine of 45 is r over 4t, which means range is 4 times that 0.577, which is right here, times cosine of 45. And you'll get 1.633. So we have a little bit of discrepancy in these two numbers. One's a little below 1.63 and one's a little above 1.63. So for our purposes, this is perfectly fine because we're not trying to get to the moon. But think about, what if this was a kicking contest, all right, and whoever kicks it the farthest wins, $1 million. Well, the person, which one of these is measuring? How are we measuring it? Are we measuring it with some sort of camera that picks these things up, etc.? And so this discrepancy, that means somebody, to say they're both 1.63, that's not a tie when one of them is 3 1,000ths farther along, which in this case would be 3 millimeters. So the winner would be 3 millimeters farther along than the loser, who's 4 millimeters behind that. It's not much to talk about, but millimeter's a millimeter. So this is small beans for us because the models work. The modeling on paper with the displacement vector triangle works. The modeling in Python works. They're on par with one another. And since we're not going to the moon or having an Olympic judging contest, this will work just fine for our purposes. All right, vertical speed. Now, you can't get two data points at the same time in Python. So what I've done here is I've overlaid some graphs. I took 2 screenshots and pieced them together. Ended up being easier than I thought. And so we have these data points that we can look at, all right? And why pick this halfway point for vertical speed? Because what I'm going to be able to do here is do the max height again. Okay, I can do vertical displacement, and so I want to be careful with the lingo here, because from a graphical analysis standpoint, so I'm also trying to tie everything in the course together, this is going to be, let me say, half vertical displacement is going to be max height. Now, vertical displacement, if it starts at ground level and ends at ground level, then it has 0 displacement. In the Python thing, it actually had a very small displacement because it it started at 0.06 and it landed at 0.05, so it had a negative 1 centimeter vertical displacement, even though its path was much longer and even though the max height was much longer. So there's these pieces of jargon. So physics has its jargon, chemistry has its jargon, biology, medicine. Fill in the blank, you name the field, it's got its piece of jargon that you have to know how much that corresponds to the way everyone else uses it, whether they're a scientist or not, because communication. And so you don't make mistakes. And so I have to do half vertical displacement because at the peak, for a moment, the y velocity, which is what we're looking at, Vy, is 0. It started off, the y velocity was more than 0, and as gravity worked on it, it got to 0, and then it picks it up again as it falls to the ground, okay? And so that's why you have this constant acceleration that's decelerating the ball. That's why we have a negative slope graph. So I wouldn't do the whole thing because I would trick myself into thinking that there was twice the max height for vertical displacement. And so it's important conceptually as much as it is mathematically to use the graph properly. And so easy kind of mistake to make. And so this vertical displacement, so delta H here will be 1/2 of this delta V times delta T. So this is just right back to that graphical analysis stuff, okay? So H would be the half delta Y, so to speak, and I don't need that crazy, more complicated equation. And I can just say, oh, well, it's going to be, the delta V is this 2.828, I'll leave the rest off, minus this 0.006, which is essentially 0, times the peak height, half of the time of flight. And so here I get, what do I get? I get 0.4063. But hopefully remember, we already found out the max height was more like 0.468, 467, somewhere in there. And why do I have a different answer here? Well, this particular way of getting the data forgot about that it started at 0.06, and the reason it forgot about it is because it's not in this graph. I'm taking this data, this simulation real-world data, and forcing it to be theoretical, which means it's off because this particular set of data didn't account for something else in the system. And so it's more like 0.4663. This is a much, much closer to the prior answer of, what was it, 0.4681. All right? So this is possibly the most important piece of this compare and contrast between the two sources of knowledge, the theoretical side and the data side, if you will, the real world side, and how they correspond to one another. And guess what? I don't care what other field it is, the same thing obtains. There's the textbook way of framing the problem, which is almost always, well, it's theoretically correct, but inevitably fails to account for something else in the real world system, unless you say, okay, I'm going to talk about friction too, and I'm going to talk about air drag, and I'm going to talk about whatever, okay? And science works that way. Science, medicine, all that stuff. And so, but again, it's close enough, and we know that we forgot, or that this particular piece of data has no idea about that starting point. Just like if I didn't tell you where this came from, you would have no idea that there was that thing to add in. And it would be easy to forget because this is pretty far removed from the output that we had. We've done a bunch of math before this, so it's easy to push that little bitty piece of data away from all that simulation stuff. So again, that skill, that's a skill that you need to, this accounting skill for the data versus the theory of your whatever your craft is. All right, last thing on this thing here, this horizontal speed, since it's an x direction, and we know that the area under a speed versus time graph is a displacement quantity. So this area in here, this is a displacement, because meters per second times seconds is going to be some number of meters. So we did a bunch of that before, okay? And so now we can double check it again. So we know that our delta x, which is our range in this case, we know that's going to be, and it's going to just be Vx times delta t. Well, that means our range is going to be 2.828 times the 0.577, and that means the range is going to be I think it's 629 again. Yep. Which matches our prior theoretical thing, which was very close to what the graph, another graph told us. So we have a theoretical validation of our simulation that accounted for the physics in terms of force and motion in a way that's different than our traditional projectile motion analysis. And again, every area of science has this sort of the theory versus practice. There's almost always another way to model it. And sometimes that other way to model it is easier or more informative than the alternate method. And that's why we spend so much time in school as we make our way towards some sort of career in the sciences, is because we have to model, or we have to build the models, or we have to recognize the models, or just understand the data discrepancy from the science to the reality, because science isn't reality, physics isn't reality. It's a way to describe reality, and the better you describe it, the more accurate it is. All right, so there's lots of things piling in on this relatively simple example, at least in terms of the math we did today. Of course, the simulation is a little bit more complicated. All right, so I'll leave it